Hi everyone, this is Ravleen Kaur and today I'm going to present my project topic, Robust Feature-Based Tracking Algorithm. These days, many object tracking algorithms are prevalent. So there is one way of tracking the object is by feature tracking. Feature tracking is basically the abstraction of the image information by using features. At every point of the image, we make a decision whether that point should be selected as a feature or not. So all those features are basically the subset of the image pixels. There are many feature-based tracking algorithms present these days. Most of them involve high computations and thus is very computation intensive, and thus it's not suitable for real-time systems. We want a system which algorithm which is suitable for the real-time systems. Thus, we are creating this robust feature-based tracking algorithm. This algorithm will be definitely simpler and involves less computation, thus making it suitable for the real-time applications. While choosing any algorithm, there are certain steps that need to be followed. We need to decide the motion model first, and the motion model that I'm using is Shitomasi's motion model. It involves two motion models, the translation motion model and the fine motion model. The translation motion model basically considers the linear motion of the object with the at a distance difference delta x. And while this motion model is highly accurate for the consecutive images, but over a long frame sequence, this model loses many of the feature points. To overcome its shortcoming, we have a fine motion model. This fine motion model is used to detect collisions in the current frame with respect to the first frame. It also considers the rotation and the scaling effects, etc. Thus, making it more efficient, but it is more complex also. So therefore, this Shitomasi model is a combination of a translation and a fine. It uses a translation model for the small interframe differences, and for the over the sequence it uses a fine motion model. Second is segmentation. Segmentation is basically extraction of the foreground and the background objects, and then we create mask for after the segmentation. Segmentation is basically done by giving the probability to the each pixel in the image. If the pixel is present in the foreground, the probability we give probability equal to 1, and if it present in the background, we give the probability equal to 0. Now after that segmentation, we generate a derivative mask, and then derivative mask is convolved with the image I to form Ix and Iy. These Ix and Iy are further convolved with a Gaussian filter to form G as a matrix. G matrix has Ix, Iy as and the ix into iy, ix square and iy square as its elements. Then we calculate determinant and trace to generate the cx, which is basically quality factor. This is the Harris-Corner condition, and if this quality of the feature point is greater than the threshold, then we select that feature point, else we don't select it. Then is the sum of square difference criterion that I'm using in this project. All this I'm discussing because we are using all this in the project. The sum of square difference criteria is basically that assumes that since Andal is translation motional, basically the feature tracking is the tracking of the x and y with respect to the time t, and the variation is dx, dy and dt. So the difference, lesser the difference between those points, more will be the similarity. So this is the one way to determine the feature point, by determining the similarity with the difference criteria. Then is the Lucas-Kernot feature tracker, which accounts the optical flow as a similarity parameter. So we find a V in the second point V in the second image J, which is similar to the eye of U in the eye of U, where I is the first image. So since this Lucas tracker and SSD, they work well for the small sequences, but over long sequences, they do not give that accurate results. And also, they are not robust, so we implement the pyramidal implementation of the Lucas tracker. So basically this and SST combined, this pyramidal implementation is basically, we calculate the linear decomposition of the image at various levels, and then at every level direction vector, that is D, is calculated, right? And then overall direction vector is calculated. That direction vector at each level gives us the small window size, and the direction vector at the large window gives us the overall vector size. Thus it accounts for the both accuracy as well as robustness, which Lucas Cunard tracker couldn't detect. So this is a good balance of accuracy and robustness, and this is what that provides this algorithm robustness. This is the pyramidal implementation. Here we input first image, then we select feature points, save feature points. Then we input second image and track feature points. Then we delete the lost feature points and save the track. As we can see, this is a recursive process. This recursive process, basically it helps us in giving the more number of feature points, thus making it more robust, and also it is less computation intensive, and it is computational efficient, that is it's fast, thus it can be used for robust and real-time systems. So this algorithm is basically divided into two parts: feature selection and feature tracking. Feature selection is the one that I have explained before, using Harris corner criteria, where we select the quality of, where we calculate the quality of each feature point, and then if the quality exceeds the threshold, then we select it, and else we reject it. Also, we can consider one more thing, that the minimum spacing between two feature points must be some greater than some fixed distance. Then there's a feature tracking, which is done by the pyramidal implementation, which I have already explained. Now I implemented Lucas Cunard feature tracker. I inputted a sequence of images where the object was basically rotating, and the output is generated as follows. As we can see, the blue and the red dots, they are representing the feature tracking. So as we see, it's very accurate for the small window size, but it doesn't consider large window size. Now I'm implementing pyramidal implementation, and I'm inputting the video as and I get a sequence of images as a result of the pyramidal implementation. I can, here is my MATLAB. As you can see, as I'm pressing, the sequence of images are appearing. So, yeah, as I was discussing, feature-based is definitely more robust. As you can see, it's tracking many feature points over the time, and also it considers the far featured track points, thus it considers the large window size. So problem faced is that I wanted to generate the video as an output, but I couldn't. But yeah, I did get the sequence of images at the output. The conclusion is that pyramidal implementation is definitely more robust than the Lucas tracker algorithm, as we have seen. It's accurate, but it is used for small window size. Pyramidal includes the large window size, and it is more robust, and thus it takes less time. And also it selects and track features that are far apart. Thank you.